Hi guys, just giving an update about my double cross antenna that I published a few years ago. I'm hoping to share my experience with this type of antenna over the past few years and some changes I think need to be made going forward. In addition, I'll also be talking about the use of a Sawbird amplifier. Firstly, understand there are two different types of satellites I capture weather data for. The American NOAA satellites that transmit an analog signal like a fax machine, and the Russian Meteor satellite that is a digital signal that must be decoded. In the video, I documented making a satellite out of aluminum to increase its rigidity as it was located outside. This worked good enough to capture images from the NOAA satellites, but unfortunately for reasons that are still unknown, did not capture digital images from Meteor very well. There is still lots of noise and captures were mostly unusable. Since then, I've constructed a second antenna made from PVC instead of aluminum to try to fix the issue, and will be discussing the differences decoding the weather images. I've also obtained a Sawbird amplifier which is designed to amplify these weather satellite images as well as act as a filter for everything else. In this video, I'd like to show you my results as well as my findings during the past year or so.
The leftmost element, you can see that some of the duct tape has come loose. It is quite rusted, and if you, for example, looked on the bolt near the antenna plug in, you can see it's quite tarnished and rusted, although the aluminum is actually held up quite well. The excessive wire has probably not helped in the signal quality. Now, the elements themselves, I don't actually think they are at the right angle, because you can see they're sort of all over the place. Here's the new antenna. This is actually the TV antenna, and it's simply put on top. So here's the antenna close up. Now, the design is actually very similar to the old antenna, how you have two hose clamps that are clamping the antenna itself to the pole. The way I attached the elements is by having the wires run on the inside, but instead of it coming out, I actually have it connect on the inside. Now, as you can see, there's two bolts here. On the previous design, I only had one bolt here and one bolt here, except that wasn't very good because it caused it to tilt and it wasn't very secure. So what I did instead is actually have three bolts, and that seems to make it a lot more secure. And with that third screw, I've actually attached it to the elements using the third screw using little eyelets. Now, this was actually suggested by a viewer, so thank you whoever suggested that, but that seems to be securing it really well, and it also allows it to be a lot more waterproof, and it seems to have prevented quite a bit of corrosion, although there is some sort of blue, I'm not sure what that is in there. Seems to be some sort of blue marking on the actual wire. Now, the angle of these are, because they're not plastic, they're PVC, the friction between this piece and this piece is a lot more, and so it means that the wind is not going to knock it off as easily.
Alright, so now we're going to have a little bit of an investigation of the results of the antenna that was installed. As you can see, this is the image that I captured with the wooden antenna, and this was my first day capture, and to this day, this is still my best capture. In this image, this is using the metallic antenna that was made from the video, and from the start you can see there are a few issues. There are gaps in the signal here, there's noise, and if you compare it to the first image, the field of view that the antenna was able to capture is very different. Now, this may just be because it was in a different location on the roof, I don't know, but it's missing a whole chunk of data to the north and to the south. This is another image that was captured, and again, missing data and lots of noise. And these images are okay. They're probably, you could probably deal with them. Oh, for crying out loud. And generally they're just not that bad. But when you look at the following images that came out, they're not. There's a lot of noise. The previous ones were quite cherry-picked, but if you actually look at the whole result of what we get, then you see there is lots of images where there's a lot of noise, especially on these tail ends of the signal. And some signals are just outright, some images are just outright unusable. So these are okay. I haven't bothered to rectify this one, but so they're okay, but I mean, like, these were night captures, but I mean, like, those are completely unusable. And then, like, this one or this one, they're just, they're basically unusable at this point. And, like, I honestly don't know why. Like, the signal sometimes just doesn't even get captured. Like, the signal is there, but it just doesn't actually lock on. And I'm not 100% sure why. And I don't know if it has something to do with the antenna being metal. Um, And these are just, again, some cherry-picked examples. And if you look at this one, like this, like basically the whole image was just missing. Now, eventually I did find a piece of software called Meteor GIS, which what it did was it looked for the signal and it captured it from one of the TCP connection, and then it did some rectification work on it. So as you can see, this is a joint. It actually stitched the two images here, one over New Zealand and then one over uh, mid-east Australia, and it's gotten rid of a lot of the noise. Like the original images here had a lot of noise. Obviously, it can't produce data that doesn't exist, so this section here is just blank. But these images, it actually looks quite good using this software. And the software, Meteor GIS, also perspective adjusts it so that it can fit on the globe. As you can see, it's sort of arched. And it's quite decent quality. It's not as good as the original images, but it also puts your location on the map. And it overall does an okay job, but if the data isn't very good, then there's not much it can do. Like in this image, it just the data, the just antenna just didn't pick up this signal, I guess. It may have just been there and it just decided not to lock on. Again, I don't know why. And these images were all with these examples were all with the metallic image. Now, I went to Canada in 2019 and I brought with me a portable antenna similar to the one I made. I made it out of retractable antennas and it was just made of wood and it was compact enough I could fit it in my suitcase. And here are some of the results from those images. This was using a wooden antenna. Now, the location of which I put the antenna was not in a location which could get very good field of view, such as why these north sections and south sections are completely missing because they were houses. It was quite an urban area. So these were quite interesting because I hadn't seen images from this area of the world before. And here's a night shot, which is really cool because you could see the transition between day and night and day and night. And again, missing data, whatever reason, maybe a cloud went over or something, I don't know. And again, missing data. This was quite a good image here. And yeah, to be honest, these images look a lot better than what my metallic image captured. And I actually don't know why. Because I just don't know if it's the environment or the wooden antenna or what. But like, look at this image. This image, it really shows the colors. Like you can see the sun partially reflect off the water and the clouds. And there must have been some noise here because you can see some blurriness and it's tried to replace the missing data. And as you can see, this on the left is the metallic antenna using the 137 megahertz, and on the right is the PVC on 137 megahertz. And this, you could look at the noise floor here. You see the noise floor is between negative 55 and negative 60, whereas using the PVC, you could argue it's between 50 and negative 55. So you could argue it's maybe about negative 5 dB higher. I mean, again, I don't really know if that's saying much. You could look at these these constant, these seem to be just constant. I think these are transmitted by the satellites because they only seem to appear when the satellite's over. But you could compare these and say, oh, look, these are significantly stronger between the PVC and metallic antenna. But and if you because the signal from the Meteor satellite does seem to vary a lot, depending if like a cloud goes over, whereas these are pretty constant. It's a bit hard to say, but it does seem the PVC antenna is significantly stronger here. If you look at the time, they're a few minutes apart, so these are a bit more closer in time, 704, 705. If you look at the signal here, again, you can just see it may just be because the satellite came out of a cloud or something, but it just seems like the signal is way stronger on the PVC antenna. And I haven't gotten a lot of results, but the thing is, here on the metallic antenna, once the satellite finally come over, yeah, it looks stronger. But then you look at the PVC antenna. Again, this is a minute apart, and you can see on the color of the waterfall, the amplitude of the signal is significantly stronger. So I'm not really sure if you could draw a meaningful conclusion from these results. My conclusion maybe is that the PVC antenna does seem to produce significantly stronger signal compared to the metallic one, but that could just be because the cable, like, could just literally be the cable. I don't know. The cable from the PVC antenna is one I made myself, or I soldered on the joints, whereas the cable from the metallic antenna, the aluminum one, is one I actually bought and was pre-made, pre-crimped, and everything. And the difference between having a weak signal like this and a strong signal like this can be the very thing that determines where your image starts, whether it starts when the satellite is 5 degrees above the horizon when it only just comes above the trees, or whether it starts 25 degrees above the horizon and your image ends up half the size and you only capture half the image because the satellite signal itself is so weak. Whereas if you have a really good antenna, that weak signal becomes usable at the lower elevations. Whereas once you reach a certain elevation, once you reach a certain signal strength, it actually doesn't increase the image quality at all. What it does do is increase the stability of capturing the image. If you have a strong image signal like this, the stability of capturing it is extremely high. As soon as a cloud comes over, if you have a weak image, it just loses its lock. However, if you have a strong signal, if it goes down a bit, it still locks on, it's still capturing data. There's less noise with a strong signal. It doesn't increase image quality though. I would now like to discuss a capture that I just did a few moments ago in regard to a amplifier filter that I bought. This is a SAW filter designed for 137 megahertz. It's Sawbird Plus, specifically for the NOAA satellites. Now, this particular filter requires external power, obviously, and I just powered it off a USB phone charger because it allows USB as a input. Now, the result that I got, the difference that I got from the amplifier is disappointing because there doesn't actually seem to be that much of a difference, because the static portions are where I unplugged and plugged the filter in, because if you just unplug the power, you get no signal whatsoever. It doesn't just pass through, it just actually disconnects. So you actually have to remove the filter. Now, so that's why there's a period of static. Now, the changes between them are, like, for example, this would be with a filter, without a filter, with a filter, etc. They don't seem any different. I mean, like, you could argue there's a little bit of static difference, but honestly, it's down to like the clouds and stuff. Like, it might be better on the tail ends, but with these analog NOAA satellites, as long as the signal is good enough, you're going to get a good picture. Now, I actually took some screenshots of the actual results. So as I was capturing the data, this was with an amplifier. Now you can see the noise floor is about -40, and without a amplifier, the noise floor is a little bit higher than maybe 43. It doesn't actually make that much of a difference. And if you look at this constant signal here, it seems to be just under maybe -16 dB. Here, it seems to be just under negative, just about -21. So it seems to make about maybe a 5 dB difference. Uh, that's it's not for these analog satellites. It's not a lot of signal difference. Like you can actually see the difference in these pictures, the color between the signal. You can see the one with the amplifier is stronger, and the one without the amplifier is weaker. And if you go back and forth, you can see there is a large color difference. If you look at the picture itself, as I said, like it's a very small difference, and in my opinion, an amplifier, I mean, it's hard to say because an amplifier might be useful in some situations, but I would argue that the more important factor is probably your antenna design. Now, I like to investigate the use of the filter for the meteor images. Now, as you can see, this is the result from a capture just this morning, and you can see the top portion is all noisy, and then it sort of clears up, and then it just has no information whatsoever. Normally, these results should be significantly larger. I'm not going to bother going through the process of rectifying these images because I really can't be bothered. What I found interesting was that when the actual signal came just into view, the Meteor demodulator almost instantly found the image and locked on. And that was really surprising to me because normally the images require a lot significantly more actual signal before it can get a lock. And it looked on with quite a small signal. So this might be, I don't know, maybe like -35, and it looks like the signal was only -30. And I found that really interesting because that's not normally what happens. Now, it has happened before where it gets a really small signal. It has also happened where I've gotten a really strong signal, and for whatever reason, the lock just does not work. Sometimes you have to adjust the frequency so that you can see in the middle of the meteor signal here, there's almost like a solid line. You have to make sure this red line is exactly in line, and you may require adjusting the frequency. I believe that's due to Doppler shift, and this slowly shifts to the left during the course of the pass, and or to the right, I think, depending on which way the satellite is going. What I found really weird is that the signal seemed to mostly keep track during the course of the pass. You can see it got stronger here, but then it also got really weak. It's quite intermittent, and you can see here it's quite strong. And then eventually it does fade out to nothingness. Here you can see it actually lost the lock. And here it got the lock again. Look, there's like basically no signal, but it's somehow locked. I don't know how that even works, but somehow, and then finally this is without any signal. You can see like the remnants of the signal on the waterfall here, but like I don't even know how this is still locked. And this was using the amplifier. I didn't bother using no amplifier. I kind of was curious to know what the result would be. As you can see here, result it's not amazing, and this is using the metallic antenna as well, which probably has something to do with it. In conclusion, it does seem that by using a metallic frame for the antenna to increase its rigidity, it may have the side effect of causing some sort of interference, which resulted in worse digital images than before. Using a PVC antenna resulted in increase in signal. Although it's important to consider other factors like wire run, current connectors rather than change of material, it's also possible that the metallic antenna's location on the side of a house adjacent to the garden shed may have played a factor. As the house is steel framed, the support structure in the roof may be causing a ground effect to distort its signal. It's possible these conditions, as well as the atmospheric conditions, are resulting in the signal being degraded. The PVC antenna is located above the TV antenna, away from any large metal structures apart from the house. In early 2018, my first and best satellite recording, the antenna was located approximately 5 meters in the air on top of the patio roof using a wooden frame. This is still the best result I've gotten, but I can't reproduce it. The wood may have been allowing the signal not to be attenuated or cause interference. This also seems to be backed up by my wooden antenna in Canada produced decently clean images, at least when the satellite was higher than the tree line and house line. In my experiments, the Sawbird 137 MHz filter did not seem to make a groundbreaking difference in signal quality or stability. Possibly when the satellites are close to the horizon it helps. Antenna design seems to be a bigger factor. As the PVC antenna did provide a better signal, my final outcome would be to limit the use of any metallic parts on the antenna itself except for the elements themselves. I would be avoiding using a metal frame. The PVC pipes were cheaper than the metal tubes and are easier to work with, as you can buy end caps that provide a watertight seal. Given that both my antenna designs have seemingly poor results regardless of antenna design, the only consistent good captures I have obtained is the antenna on my patio roof away from the house. I think the effect of the house's steel frame is a major factor and is contributing to the pictures not being ideal. I hope you enjoyed the video and found the outcome insightful for when you're designing your antennas.